Our last lecture began to look at questions raised by the concept of time. If you're watching these in order, then that discussion took place earlier than this one. Events seem to happen in a linear order. How far back does it go? Did time start? What was happening before that? Does it even make sense to ask? This was not a question for the Greeks. Aristotle, for example, gives us a universe with no temporal origin. The universe works as it always has. He had a picture of the cosmos, in which the universe is divided into two regions. Inside the orbit of the moon, everything is comprised of the four earthly elements: earth, water, air, and fire. These, by their nature, move in straight lines to their natural place where they remain at rest. But from the moon on out, everything is made of a fifth element, ether. Ether is a perfect element, and so everything made of it moves in a circular trajectory. Because the circle is infinitely symmetric, it's perfect, and everything in the heavens, being made of the perfect element, partakes of this perfection by moving in perfect circles. For Aristotle, natural motion comes from an internal impulse. There's no external force of gravitation. Things move themselves. They're not pulled around by an external force, but propelled by an internal impulse. The final cause of the celestial motion is the source of that impulse. It's the love of an all-perfect deity. The gods are perfect, so the planets, stars, sun, and moon, being made of a perfect substance, have a desire to represent that perfection in their motion. But they've had that desire for all time. The final cause, the reason for the motion, is perfect and therefore eternal. So too, then, would be the universe and the motion within it. No creation here. It wasn't until Judeo-Christian thinkers came to the question with a theological need for temporal origin that things changed. St. Thomas Aquinas adored Aristotle, referring to him as the philosopher. But he realized that certain elements in Aristotle would need tweaking if they were to fit with Aquinas' theological commitment. One was to change Aristotle's final cause of celestial motion to an efficient cause. In his masterwork, Summa Theologica, Aquinas both adopts and adapts Aristotle's argument to contend that God is the prime mover and therefore the initial cause of the universe. There must have been, he argues, a beginning to time. But this is a theological, not a scientific argument. The question itself was seen as theological, not a scientific question. So that sort of answer seemed appropriate. It took 500 years for the question to move from theology to physics, and it arrived there by mistake. Indeed, the mistake that put it there was what Albert Einstein called his greatest mistake. In 1916, Einstein put the finishing touches on the general theory of relativity. The heart of the theory are the Einstein field equations, which specify the way space-time must behave given the distribution of matter and energy within it. There are many possible universes whose behavior conforms to those field equations. We call these models of the theory. In considering some of the easier models to work through, the Belgian physicist and Catholic priest, Georges Lemaitre, realized something strange. They weren't stable. Except for a split second, every single model would be constantly expanding or contracting. When he told Einstein about this, Einstein thought he was wrong. Einstein's cosmological assumption was like Aristotle. Things are, as they have been, as they always will be. But the more he looked, the more Lemaitre seemed to be right. Einstein thought the universe had to be stable, yet the theory was clearly saying otherwise. The theory had to be fixed. He added a single new term, the cosmological constant. Its job was to add a force to the universe which affects nothing local, only the universe as a whole, by pushing or pulling in a way that counteracts the problematic expansion or contraction. That was 1917. Then, in 1931, Edwin Hubble produced experimental evidence that the universe was expanding. The theory had been right. What was the evidence? Almost everything in the sky looked more red than it really was. Why red? Well, Think about an ambulance driving past you. As it approaches, the pitch of the siren goes up, and as it drives away from you, the pitch of the siren goes down. That's the Doppler shift. Sound is a wave, and if you're moving towards the wave, the peaks go by more often. That means the frequency increases. Pitch is correlated with frequency, so it sounds higher. As the source of the wave moves away from you, the peaks go by less frequently, causing the pitch to decrease. Light travels as a wave also. So it's subject to a similar effect, except that the frequency is correlated with color. As something moves towards you, it looks more blue. As something moves away, it looks more red. The universe is made of galaxies that are made of stars that work in the same way. Hydrogen atoms combine with each other to make helium, and that gives off heat and light. Light of a specific color. We know what color the galaxies should be, but they were almost all redder than that. That means that pretty much everything is moving away from us. Why would everything be moving away from us? Making use of what we call the Copernican Hypothesis, we assume that we're not special. The universe must look pretty much the same from any vantage point. So, if things look like they're moving away from us here, they should also be moving away from every other point in space as well. There's only one way for everything to be moving away from everything. The universe as a whole is expanding, just like Einstein's original theory said it would. Einstein kicked himself for not having faith in the science. When you think you're smarter than the universe will always prove you wrong. But if the universe is expanding, that means it had to have been smaller in the past. And there had to be something causing the expansion. There's only one force that operates with sufficient force over long distances: gravitation. The thing about gravity is that it only goes in one direction. Now, electricity can attract or repel a charged particle, but gravitation only has one charge, one direction, attraction only. But the universe is expanding. Gravity could slow that expansion down as things pull on each other, but we need a push, not a pull. Gravity couldn't cause the expansion, although it could stop it if there was enough stuff to provide enough pull. This led to the question of the end of time. If the universe is expanding, that means there's less and less energy per unit volume. Eventually, if the universe expanded enough, that amount of energy would be insufficient to sustain any sort of interesting phenomena, including life. If there was not enough stuff in the universe would eventually die a frigid death. But if there was enough stuff, then the gravitational brake would stop the expansion and cause a contraction. Gravitation would give rise to a universe accelerating inward that would collapse in on itself. It would concentrate its energy into greater and greater amounts per unit volume until it became too hot to sustain atoms or nuclei. It would perish in a big crunch. Perhaps when the energy was sufficiently high, it would trigger some mechanism we don't know about and cause the universe to expand again. Maybe we have an accordion universe that goes out and in forever. Those seem to be the only three possibilities. It all depended on how much stuff there is in the universe. We figured out what the critical mass would have to be to cause a big crunch, and then decided to weigh everything to see if there was at least that much stuff in the universe. And that is where it got weird. Galaxies are collections of things. There are two ways to weigh a collection. If I wanted to weigh my family, I could either get a big scale and put all of us on it, or I could get a small scale, weigh each of us, and add up the weights. Those two should give me the same answer, right? It would with my family, but it didn't work with galaxies. We weighed the pieces we could see, stars, stuff that glows, which is pretty much all the non-trivially heavy stuff, and added it all up. Then we weighed it as a whole, and that number was much larger. There was something, a lot of something we couldn't see. The only thing with mass is matter, and if we can't see it, it's dark. So we called it dark matter. It's the excess weight in the universe. What exactly is it? Don't know. But that's not the weird part. Okay, so there's a lot more stuff and we have to figure out what it is. But whatever it is, we know how heavy it is, and that's what we needed to determine how much this overstuffed universe was slowing down and if it was enough to stop the expansion and cause a contraction. Turns out that the universe is like my 9th grade English teacher explaining how to write a formal paper. No contractions. We tried to measure how much the universe was slowing down as a result of all the light and dark matter, and guess what? It wasn't slowing down its expansion at all. It was actually speeding up. What? There's only one force that works over a long distance, and it's gravitation, and gravitation only attracts things. Gravity is only capable of slowing down the expansion. How could it possibly be speeding up its rate of expansion? Don't know, but it is. There's some other force. We have no clue what it is, but a force is the result of energy. What sort of energy? Don't know. So we called it dark energy. Every time you think you have the universe figured out, the universe just gets weirder. But we're getting ahead of ourselves. Back to the question at hand. What caused the expansion in the first place? In the 1940s, there were two theories. One sought to maintain a temporal version of the Copernicus principle. The past should look like the present should look like the future. There was never a unique cosmic event and never will be. The universe just chugs along as it always has and always will. It was thus called the steady state theory and was developed by Fred Hoyle, Thomas Gold, and Hermann Bondi. According to it, the observed expansion of the universe forces us to give up the principle of conservation of mass and energy that we think is a fundamental truth. We must instead adopt a new principle of conservation of mass density in the universe. As the universe expanded, hydrogen atoms would just pop into existence, keeping the mass density of the universe the same, no matter where, no matter when. A competing theory developed by George Gamow abandoned the Copernican assumption and held that the past did not look like the present. If things are getting bigger now, they must have been smaller then, and something must have caused them to expand. We need to be careful with our language here. When we talk about universal expansion, we're not talking about blowing up a balloon in a room. The universe is not a thing, and it's not expanding into a bigger container space. We're talking about an infinite universe wherein the space-time itself is expanding. How can an infinite thing expand, and how can it expand if it isn't expanding into something else? Okay, so imagine watching this lecture on a big screen TV. Now, imagine a bigger screen TV. Now, imagine watching it on an infinite screen TV. If you had an infinite screen TV and got real close to it, you would see that the picture is made up of pixels. Because it's infinitely wide, no matter what pixel you look at, there's always another one to the left and another one to the right. Since it's infinitely high, there would always be a pixel above and a pixel below, no matter what pixel you pick. Now, watch the pixels closely. They start moving apart from each other. Images of me slowly but steadily get larger. Focus on the bridge piece of my glasses. Over time, it gets bigger and bigger and bigger. Here we have an expansion on an infinite plane that always was and always remains infinite. Now, just do that in 4 dimensions. But one difference with the metaphor is that it's not the stuff in the universe that's expanding, but the space-time of the universe itself. So, what then caused the expansion? The steady-state advocates tried to mock the idea that there was a unique event in cosmic history by saying, oh, so you have a scientific theory based around a Big Bang? The insult was so catchy with its alliteration that it stuck. And so the view became known as the Big Bang theory. Which theory correctly described the nature of the universe? The one with constant creation of matter, or the one that started with an initial seeming violation of every known law? The case was settled by accident, but almost not by accident. At Bell Labs in New Jersey, two researchers got the scientific flea market bargain of all time. They got a hand-me-down radio telescope. The government was using it to do some work with weather balloons, and when they didn't need it anymore, they gave it to Arno Penzias and Robert Wilson. They prepared to use their new tool and set about calibrating the telescope. To their frustration, there was some background noise they couldn't seem to get rid of. They tried to figure out where it was coming from, but no matter where they pointed the telescope, they still got it. They ruled out man-made sources around them. They ruled out the sun. They found a pigeon's nest in the telescope. Clean it out. Nope, background noise still there. They cleaned out the pigeon droppings. Who said that science isn't glamorous? Nope, still there. 30 miles away at Princeton University, physicist Robert Dicke realized that one of the differences between steady state and Big Bang theories was testable. If Big Bang theory was right, then there ought to be a background radiation, an energy fingerprint left everywhere in the universe. He and some colleagues did the work to calculate what it should be and came out to a figure. To look for it, they would need a radio telescope. This made Dicke happy because he was a pioneer in radio astronomy, having not only made discoveries, but invented the Dicke radiometer, which was a major advancement in the instrumentation. He and his Princeton team were starting the process of putting together the funding and the team to build a radio telescope to look for the ever-present, non-directional background radiation. When Penzias and Wilson told a colleague about the problem with their background noise that they couldn't get rid of in their radio telescope, the friend told them about a paper he had read from Princeton that wasn't published yet, about constant, ever-present background radiation that should be everywhere. They got a copy of the paper. After reading it, they realized what they had tripped over and what they had done to Dicke. They invited him out to Bell Labs to see their setup and examine their data. In a gesture of generous cooperation, they both published their papers together as back-to-back articles in the same journal. Dicke and his team published their theoretical calculation, and then Penzias and Wilson published their data confirming the calculation. Big Bang theory was experimentally verified. It won the battle with steady state, and Penzias and Wilson, but not Dicke, were awarded the Nobel Prize in Physics. The ultimate irony, adding insult to injury, the radio telescope Penzias and Wilson were gifted and used to make their accidental discovery for which they won the highest honor in science was made with a Dicke radiometer. So, we have a theory that says that the universe is expanding because at some time in the past there was an event that caused it to start to expand. As it expanded, it cooled, and as it cooled, the situation allowed subatomic particles to form. Eventually it became cool enough for the subatomic particles to hold together, forming atoms, then cool enough for the atoms to bond into molecules, and ultimately cool enough to give rise to Elvis. But the really cool part of the universe is not the part where the universe is cool. The philosophically interesting aspect is at the other end, the Big Bang itself. What does it mean to have a scientifically validated theory that postulates a Big Bang, a seeming origin of time itself? Pope Pius XII contended that it means that science has been able to provide empirical evidence for the existence of the Christian creator God. It's worth noting that modern exponents of the natural sciences consider the idea of creation of the universe entirely reconcilable with their scientific conception, and indeed are brought to it by their researches, he said. The Pope held that the confirmation of the Big Bang theory was not only consistent with the theological notion of creation ex nihilo, that is, creation from nothing, but leads to it. He sketches the picture of the early hot universe as a place wherein the energy density was too great to allow for matter, and how the expansion led to cooling which allowed it. That science brings us this picture, which leads to an obvious question, which the Pope states. The eager mind, in its search for truth, rightfully insists upon asking how matter came to be in a state so unlike that of our common experience today and what preceded it. One waits in vain for an answer from natural science, which honestly declares that it's an insoluble enigma. Physics can get us to the existence of the Big Bang, but we have to ask what came before it and what caused it. Those questions are questions science cannot answer, but which do have answers. The Pope said, "Indeed, it seems that the science of today, by going back in one leap millions of centuries, has succeeded in being a witness to that primordial fiat lux, when, out of nothing, there burst forth with matter a sea of light and radiation, while the particles of chemical elements split and reunited in millions of galaxies." The Big Bang Theory uses science to get us back to the instant when God created the universe. This interpretation of Big Bang cosmology is opposed to one of the giants of 20th century philosophy of physics, Adolf Grundau. Born to a Jewish family in Germany in 1923, he fled with his family from the rise of Hitler. He would, however, soon return, only this time with the U.S. Army as part of a crack squad of interrogators. Being smart, tenacious, and German being his native language, he personally interrogated major Nazi figures, especially those who had been academics. After the war, he trained in philosophy of science, became one of the early huge figures in American philosophy of science at the University of Pittsburgh, where he was one of the founders of their Center for Philosophy of Science. He wrote almost 400 articles, and his major work on philosophy of space is so large that we in the field just refer to it as the cube. He turned his talents to the claim that Big Bang theory validates the biblical account of creation in his article, The Pseudo Problem of Creation in Physical Cosmology. The term pseudo problem comes right out of the logical positivists. The idea is that there are real questions and these demand our attention, but then there are pseudo questions. They look like questions, they sound like questions, but they aren't questions. A question is a request for information. If the information requested does not exist, then what you have is not a real question. If you ask me, "Steve, what color car does your sister drive?" the debate could go on forever without end. Not because this is a deep perennial question, but because I don't have a sister. Sounds like a question, but it's really a pseudo question. That is exactly the status Grundau assigns to seeming questions like what happened before the Big Bang, what caused the Big Bang, and is the Big Bang a scientifically sanctioned case of supernatural creation of the universe? Those contending that Big Bang cosmology provides good reason to believe in creation are, he argues, committing at least one of three sorts of fallacies, that is, logical mistakes. The first logical error is the inference that's made in which it's asserted that because everything is caused, there must be a cause to the universe. When we ask what caused the Big Bang and then look for an answer outside the universe, we're misusing the notion of cause. In the premise that everything is caused, we're looking for causes within the universe. If I look at a cake and ask for a cause, I'm asking what in the universe brought together the flour, eggs, milk, sugar, and shortening that were in the universe in order to bring together this delicious tribute to my birthday. And it's a reasonable question. But the fact that all questions have such answers does not entail that the Big Bang had a cause or that the existence of the universe has a cause, because these are completely different sorts of questions. And it certainly does not follow, Grundau contends, that creation from things you can buy in the grocery store entails creation from nothing by the will of a supernatural being. The second group of reasoning errors that Grundau points to in arguments that take Big Bang cosmology to give rise to claims of extra-natural creation are questions of the sort, what happened before the Big Bang, or what was happening before time t equals 0? These questions seem to make sense to us because we're smuggling in Newton's view of time as a linear stacking of moments. In this common sense picture, every moment has a moment before and a moment after. But in the case of the Big Bang, we're not talking about events in linear Newtonian time. We're talking about the origin of time itself. To ask what happened in the time before time is self-contradictory. It seems to make sense when we come from a place of classical time, but not if we realize that we're talking here about the origin of time itself. The third group of fallacies that Grundau claims are implicit or explicit in arguments from Big Bang cosmology to divine creation is that since science can only deal with that which is accessible to the senses and reason, that is, that which is part of the universe, and since the cause of the universe has to be external to the universe, then the cause of the Big Bang has to be beyond the scope of science, since it's beyond the scope of reason. Science can only give answers that the human mind can comprehend, but God is beyond the comprehension of the human mind and therefore beyond the reach of science. Science gets us to the Big Bang, but faith gets us the rest of the way to the divine. Grundau argues that if a belief is beyond science because it's beyond human comprehension, then it must also be beyond faith. One can only have faith in a proposition one understands. Faith is required for that which one can believe or disbelieve, but for which one lacks evidence. If this is beyond the scope of science to obtain evidence because it's beyond our comprehension, then, he contends, it's also beyond our ability to believe on the basis of faith. Take away these three moves, and, Grundau argues, the arguments that Big Bang cosmology leads to divine creation go away too. Is this right? That's the fun of philosophy. Philosophy deals with the big questions, but philosophy of cosmology deals with the biggest ones of all.